Hi everyone, my name is Neha Kadam and this is the second lecture on electronic communications. In this lecture, we are going to learn about signal analysis. Let's get started. So what is signal analysis? To learn about signal analysis, we need to know first what signal is. So signal, it is an electrical current or voltage that either represents information or performs some useful function. Most signals are alternating current, sine waves, or combination of sine waves. Signal can be viewed in either time or frequency domains. So as you can see here, signal analysis is the study of composition of electronic signals. Electronics technicians view signals in two primary domains, time domain and the frequency domain. And some signals they are unwanted like noise, and noise is produced both inside and outside of the circuit. For example, radio receivers are especially sensitive to noise as they amplify tiny signals from receiving antennas. So all the signals we know they have a time and frequency domain representation. To see in time domain, we normally use oscilloscope, and to see in the frequency domain, we use spectrum analyzer. Now moving on to the next slide. Here you see a time domain representation of a signal, and this graph which you see over here has been taken from a oscilloscope. And here it says oscillogram is a time domain representation of a signal. The signal is shown as it happens. So here the time base of a scope moves the dot across the face of the screen, you can see here, at a constant speed. Vertical deflection moves dot up and down, and horizontal moves the waveform from left to right. Now let's move on to the next slide. This slide talks about frequency domain, and it says a spectrogram is a frequency domain representation of a signal. The spectrogram shows the frequencies present within the signal. In other words, we can also say an instrument that shows the frequency domain content of signal is called spectrum analyzer. Now, you might think, why do we need to use the spectrum analyzer? So the spectrum analyzer is used to separate the desired carrier signal from all the others on the air. And secondly, there is finite amount of space on the bands in which to operate radio transmitter. Transmitter use this space similar to a parking lot space. By looking at a radio transmitter signal in the frequency domain, we can determine the bandwidth. Now you might think, what is a bandwidth? So bandwidth is basically the amount of frequency space taken up by the signal. You will see any distortion in a sine wave, it will cause new frequencies, and those frequencies are called harmonics. Distortion of a sine wave is often much easier to spot on a spectrum analyzer when compared with the oscilloscope. Now moving on to the next slide. Here you see a pure sine wave signal which is having a 10 volt peak and 20 volt peak to peak. The sine wave is the only pure waveform. A sine wave contains only one frequency. What would the sine wave above look like in the frequency domain? So this is how your pure sine wave look like on an oscilloscope. And now we're going to see how it will look like on a spectrum analyzer. That's how it looks. On a spectrum analyzer, the 10 volt peak sine wave looks like this in the frequency domain. Notice that the RMS value of the voltage is shown here. So this value you see of the signal is your RMS value of the voltage, and here on the vertical plane, on the horizontal plane, you see the frequency which is set at 1 kilohertz. If we go back to the previous waveform, here you see 1 millisecond was our time and 10 volts was our peak. But when you look at on the spectrum analyzer, you will see your RMS voltage represents the signal, and here this represents your frequency of the signal. Now comes the non-sinusoidal waveforms. Non-sinusoidal waveforms, they are any periodic waveform that is not a pure sine wave, will contain the following components. A DC component or DC level, a fundamental sine wave at the same frequency as the composite waveform, a collection of harmonics which are sine waves at multiples of the fundamental frequency. Many waves contain an infinite number of harmonics. In other words, we can say that these are the complex waveforms, and the example of these complex waveforms would be like your square wave, triangular wave, sawtooth wave. These are all complex and periodic signals, and we say that they are complex because they contain more than a single pure sine wave. If we talk about electronic communications, then you would also likely to measure some of these in human voice, in musical instruments, in digital data. These are all complex waveforms. Speech and musics are basically very hard to predict because they are not periodic. And all these three components you see here are basically obtained from the Fourier analysis. And the Fourier analysis says that any periodic mathematical function, we can say electrical signal, could be represented by the addition of an infinite series of sine and cosine waves plus DC level or average. And that's how we get all these components. In this slide, you see the square wave. And in this square wave, we have 1 volts peak and 2 volts peak to peak. And the time is 1 millisecond for one cycle. The square wave is a common non-sinusoidal waveform. What might it look like in the frequency domain? So here the representation which is shown here is maybe through the oscilloscope, and this is how it will look like. But how it will look like using the spectrum analyzer, this is what we are going to see next. So you see here the waveform will looks like in this form when you use the spectrum analyzer, and you see all these harmonics are there in the waveform which are represented in the spectrum analyzer. The first is the fundamental, or it is called the first harmonics at a 1 kilohertz, and at this point the signal shows 0.9 volts, and at the third harmonics signal measures 0.3 volts. At fifth harmonics it represents 180 millivolts. At seventh harmonics it measures 129 volts. So we see that all these harmonics are present in a square wave signal, and we need to notice that how these signals are basically starting to get smaller around the 11 kilohertz if you go further here. So this is why most technicians stop analysis at the 13th harmonics, which will be around somewhere here. And the 17th harmonic is very small, and it is usually barely visible. If you use the spectrum analyzer, you will see it will look like a bump on the graph. Now here you might think that something is missing here. The even harmonics you see here, second, fourth and sixth, why are they missing? The even harmonics are not present because a square wave is perfectly symmetrical. The bottom and the top just look like each other. They are mirror images. Any waveform with this type of symmetry will have only odd numbered harmonics. We say even harmonics have been cancelled out. And you see here the DC levels are basically 0 here, and the reason for that is the DC level is basically absent because average of the signal voltage is 0. Positive time and the negative time are basically same, so on an average the DC voltage will be 0, and that's why we see here 0. Now interpreting the spectrogram. The spectrogram on the previous slide shows that 1 kilohertz square wave is built from the following: a 1 kilohertz fundamental sine wave, a 3 kilohertz sine wave or third harmonic, additional sine wave harmonics at 5 kilohertz, 7 kilohertz, and so on. These are 5th, 7th harmonics. Now moving on to the next slide. Here, if you use the spectrogram, then you will see the square wave signal will look something like this. So this signal which you see here basically represents the fundamental frequency, which is at 1 kilohertz, and it measures 900 millivolts. And this represents your third harmonics, which measures 300 millivolts, and this harmonic shows your 11th harmonic, which means 11 kilohertz it measures, and so on. We have the 17th harmonic. So you see in this graph that this harmonic, which is the 17th, it looks like a small dot, and it's very small when compared with the fundamental signal. Now here you see this is the square wave, and this is how it looks like in a spectrum analyzer, and all these three are basically the combination. If you combine this, it will become a square wave. So this waveform particularly shows the 1 kilohertz fundamental signal, and this shows a 3 kilohertz third harmonic, and this one represents the 5 kilohertz harmonic. So we see here that this is the another way of looking at the square wave, and we understand that a square wave is nothing more than the sum of infinite number of sine waves, each with a frequency that is odd multiple of the fundamental frequency. And if we are asked to graph this, then these sine waves and add them together point by point, then we will get the this square wave. Now moving on to the next slide. Now here you see the triangle wave, and this picture shows the view from the oscilloscope, and in that the triangular wave will look like this. So here it says what frequencies are contained within the triangle wave shown above. So the triangle wave, the period of the triangle wave is 1 millisecond, which is 5 division cross 200 microsecond per division. If we see here, we see here this is the 200 microseconds and 500 millivolts. So here the period is 1 millisecond because 5 division cross 200 microseconds per division based on the previous waveform. Now this triangle waveform, if we see on the spectrum analyzer, it will have a fundamental frequency of 1 kilohertz. The waveform is not a pure sine wave, therefore harmonic energies can be expected to be present at multiples of the 1 kilohertz fundamental frequency. This would mean 2 kilohertz, 3 kilohertz, and so on. And because of this, waveform is symmetrical, only odd harmonics are present. So here we see, I'll move on to the next slide to see visually how our waveform will look like on a spectrum analyzer. So here you see the fundamental frequency, frequency is at 1 kilohertz. It measures 0.57 volts, and this is called your first harmonics, and here we have third harmonics. which measures 63 millivolts, and at fifth harmonic it measures 23 millivolts. At seventh harmonics it measures 11.6 millivolts. So the triangle wave looks like this is the frequency domain. To represent it perfectly, we need an infinite number of harmonics. I'll again move on to the next slide, which will show the triangular wave in a spectrum analyzer, and it will look something like this. So this fundamental of triangular wave you see is weaker when compared with the square wave. You see the harmonics are also here a lot weaker compared to the square wave, and this is because the shape of the triangular wave. Because it is very close to sine wave. Main difference is basically the addition of points in the triangular wave. You see the triangle wave points on the top and at the bottom of the waveform. Therefore, it doesn't take much energy to make a triangle out of a sine wave. And if we see in a square wave, which requires addition of much more high frequency energy that it needs to build when compared with the triangular wave, and that is the reason therefore we say that the square waves harmonic remain relatively strong when compared with the frequency of the triangular wave. Now comes the bandwidth of electrical signals, and it states that bandwidth is easily calculated in the frequency domain, and it is given by this formula. Bandwidth is equals to F max minus F minimum, where F max and F minimum are the highest and the lowest frequencies that are represented in the signal, and bandwidth is represented in hertz. So here in this graph you see a curve in which the frequency is represented, where F1 is the minimum frequency and F2 represents the maximum frequency and FR is the resonant frequency. And this is the point where the cutoff frequency takes place. So here it is important to know how much frequency or band space is required in order to reproduce the signal. The narrower the frequency range is over which the current is highest, it is called your bandwidth, the difference between them. So if the cutoff frequency occurs when the current amplitude is around 70% of the peak current, then at that point your these two frequency will occur. Now moving on to the next slide. This slide talks about filters and complex waveforms, and here we see the square wave oscillator, and which is sending a 1 kilohertz square wave signal to the band pass filter, and this band pass filter is set at a 3 kilohertz frequency. Then the question is, what will come out after this band pass filter? So can you predict what the output of the circuit will look like on the oscilloscope? So we are going to see that next. So filter and complex waveforms is continued in this slide, and here we see the view on the spectrum analyzer of the waveform, and here we see a fundamental frequency is blocked out. If you remember, the signal was 1 kilohertz square wave, which means the fundamental frequency will be of 1 kilohertz, and it is passing a third harmonics, which is third kilohertz. And why is this passing only a third kilohertz? Because this is a band pass filter and it is set at a 3 kilohertz frequency. So here the fundamental frequency is blocked out, and we can say that a band pass filter only allows signals with frequency within its pass band to get through. All other frequencies in that situation will be eliminated. Therefore, only the frequency here of 3 kilohertz can get through the filter. Or another way to say this is the filter limits the frequencies that pass so that only the third harmonic gets through. And you need to note that the output is exactly 3 times the input frequency. So here our input frequency was 1 kilohertz and the output is going to be 3 kilohertz. So it is 3 times of that, which means we can say that this circuit is basically working as a frequency multiplier. And in this particular circuit you see here can only multiply a limited range of frequencies that results in a 3 kilohertz output. The range is determined by the quality factor, which is basically your Q of the tuned circuit. And you will see these circuits often in the electronic communications. Now next comes the noise analysis. So here, one of the main problem faced by communication system users is the noise, and which can be defined it as any signals which are undesirable. And noise comes from many sources, and it is ultimately limits the performance of all the electronic communication systems. Here, if you see on the slide, it says noise is defined as any undesired signals within a system. And if we talk about analog communication system, then noise is annoying to the listener and it degrades the overall received signal quality. And in digital communication system, noise introduces bit errors into the data system, and this error can be removed by using these two methods, which is FEC and ARQ. FEC is basically your forward error correction, and it is an error correction technique to detect and correct a limited number of errors in transmitted data without the need for retransmission. Whereas this ARQ stands for automatic repeat request. It is basically a group of error which control protocols for transmission of data over noisy or unreliable communication network. So these two techniques can be used to minimize the error. And BER, which stands for bit error rate of a digital system, it is measured in units of error per bits, and improving the SNR, which is the signal to noise ratio, and we'll read about we will read about this in the next coming slide, which generally improves the BER of a system. Now I'll directly move on to the next slide and we will learn about noise in detail. So here you see how the noise sources, these are how they are classified. So they are classified into external and internal noise, where external noise consists of your cosmic noise, atmospheric noise, and man-made noise. And internal noise consists of uncorrelated noise and correlated. Uncorrelated is thermal noise, short noise, and flicker noise. Under correlated, we have harmonic distortion products, intermodulation products, nonlinear distortion products. So let's first talk about the external noise and how it arises. First, we're going to talk about the cosmic noise. So the sun and other stars in the atmosphere we see, they emits basically all kinds of electromagnetic energy, and some of which are quite useful for life, like visible light and infrared light, which is basically your heat. So this sun, it also emits radio frequencies of a wide range. So the atmosphere basically absorbs great deal of radio frequency energy delivered by the sun. So noise emitted by the sun and stars are basically called your cosmic noise. Now next is our atmospheric noise. So you know, like air moving over any object, it experiences friction, and electrical change can build up as a result. Sometimes this also cause radio frequency interference, and that is called your atmospheric noise. And another example I will give of an atmospheric noise will be lightning. So you might have seen sometimes when lightnings occur due to bad weather, then also the noise occurs. So that was one of the example of the atmospheric noise. And then we have man-made noise. So many of our machines are great noise generators, and among these are spark ignition systems in motor vehicles, power grid, fluorescent lights, and the occasional malfunctioning of a radio transmitter generally produces the noise, and that noise is your man-made noise. And then we have this internal noise. And I'll take 3 examples of internal noise. First, of a radio receiver. So if you tune a radio receiver to a blank spot on the dial, disconnect the antenna and turn up the volume, you will hear a steady rushing or hissing noise, and that is called your internal noise generated within the radio receiver circuitry. Second example would be the analog TV. So in analog TV in the past, you might have seen the internal noise occur, and it is basically visible through the snow form on the screen of the TV. So that is another example. And third example would be your digital camera. So if you shoot a picture under a dim light, then you will see some speckles on the image. That is actually the internal noise, and it originates because of the camera sensor that get and that signal, that noise is basically, it gets digitalized along with the picture information. Whereas if you click the picture under the bright light, speckles are less visible, and therefore they are not noticeable. Now here we see different noises are mentioned here. We are going to discuss uncorrelated noises. Under that we have thermal, and with this thermal noise is basically explained by these two scientists, Brownian and Johnson. And so I'm going to explain the Johnson noise here. So Johnson noise is basically present due to resistance and other passive components in the system. So basically what happens, the charges rapidly and randomly speed up and slow down, or in other words we can say that the current in the system, it basically fluctuates above and below the average value that would be predicted by the Ohm's law. So the rapid current fluctuation produces AC noise voltage, and that is called your Johnson noise. And if you want to take an example of this, you can think of maybe resistance connected to the power supply, and if there is no heat is being incident on the resistance, then the flow of current will be ideal. And if there is a heat is incident on the resistance, then you might see there will be a fluctuation in the current. So due to which some internal noise could be produced, and that is your called Johnson noise. Now we have this shot noise. So this shot noise occurs basically in the electrical elements like PN, in which we have like PN junction, for example your BJT or FETs. So what happens, each charge carriers that crosses the PN junction in those kind of equipments or devices, they basically they introduces a momentary jump in the overall diode current. And because a very large number of charges are all doing this at the same time, an AC noise current basically will be produced, and this noise current is random, just like the Johnson's noise. and Johnson's noise in the resistor. We took the example before. So all the frequency except DC are present. So factors basically affecting the short noise are the DC current and the bandwidth. And then we have this flicker noise, and this flicker noise occurs mostly due to the low frequencies. So like in the FET, if you have FET in the circuit, then that contributes to a noise which is confined mostly to the low frequencies, and the noise which it produces are called flickers. And then we have correlated noise, and this occurs due to harmonic distortion products in the signal, and due to intermodulation products and non-linear distortion products of the signal. Now I'll move on to the next slide. And this slide explains signal to noise ratio, and it is given by this formula, which is equals to P signal by P noise. And it says it is ultimately limits the performance of all communication system, both digital and analog, and it is conveniently expressed in decimal form by this formula, which says signal to noise ratio is equals to 10 log P signal by P noise. So here you see the formula here for a voltage signal to noise ratio, and it is given by 20 log V signal by V noise, and this formula has been obtained from this above formula. So if you put the value of P signal, replace P signal by in terms of voltage and resistance, you know that the formula for power is equals to V square by R. So here if you put V signal square by R, and same here if you put V noise square by R, then resistance will be cancelled out, and then you will have V signal square by V noise square. So that square portion basically can be multiplied here in the front. So 2 cross 10 is your 20, and that's why you got 20 log V signal by V noise. So we will do a couple of problems based on this formula after this lecture. Now I will move on to the next slide. And this slide talks about noise figure. So there is another way of expressing the noise performance of amplifiers and systems, and that is the noise figure. And this noise figure is basically the difference of input signal to noise ratio minus output signal to noise ratio. And for that, the example is given over here. You see this amplifier, the input signal to noise ratio is 50 dB, and amplifier noise figure is 3 dB. So you have to calculate the output signal to noise ratio. So here if you put all these values, the value of input signal to noise over here, and if you put the noise figure over here, then you can easily calculate the output signal to noise ratio. And for this particular case, it will come out to be 47 dB. So an ideal or perfect amplifier has, if we talk about, it will have a noise figure as 0 dB, which means that no additional noise is introduced, and therefore the output signal to noise ratio would be identical to that of the input. Now moving on to the next slide. Now this slide talks about the noise reduction technique. So in some cases we can actually shield the circuit to prevent the noise from getting in, and by shielding means enclosing the circuit in a metal casing or cabinet to prevent the electromagnetic energy from entering in or leaving if the circuit is potential noise producer. So to reduce the external noise in radio receiver, we can generally try to locate them as far as practically possible from the noise sources. So these are the same things which are mentioned over here. I'll just quickly read them. So metal sheeting around the sensitive circuit, same thing. Directional antennas that point away from the known noise sources, use of the minimum bandwidth necessary for the communications, use of shielded cable and connectors to prevent accidental signal leakage, elimination of excess wire length. And for the internal noise reduction method, these are some of the methods which are given. Use of low noise resistors, application of low noise semiconductors, in particular a type of FET called gallium arsenide FET, which is very popular for low noise radio frequency amplifiers, using the lowest possible resistor values in sensitive circuit. Special component layout technique can be used to reduce the inverted circuit interactions. Use of the minimum bandwidth necessary for communication. This reduces both external and internal noise. Reducing forward bias current in diodes and a transistor to the minimum practical value in order to reduce the short noise. Cooling or refrigerating the circuit to reduce the thermal noise, and this is an expensive measure. So these were some of the internal noise reduction techniques, and now I'm going to move on to the next slide. And this is the summary of what we have covered today. So I'll just quickly read this. And we covered about two domains in which we can examine the signal, which is time and frequency domain. And we learned about pure waveform, which is our sine wave, and that contains only one frequency, whereas the complex waveform, they consist of fundamental sine wave, number of harmonics along with that. And then we learned about the noise, which is and noise, we know that it is the undesired quantity in the signal, and it can occur in two ways. It can occur externally, as well as it can be inside a system, which is called your internal noise. So and then we learn about signal to noise ratio, which is a method of determining the goodness of a system's noise performance. And then we learn about the noise figure of a system, which reveals how much internal noise it adds to the incoming signals. So this is the end of the lecture. Thank you so much for watching this lecture.